the new stuff you'll just be adding by taking some notes on paper. Lab presentations, on Tuesday and Thursday morning this week, we're going to meet in the library classroom. That's the one right when you walk in the door, around the corner to the right, in 106. On tomorrow afternoon, we'll meet in here. And then our exam is on Friday. And our final exam is on Thursday, 3:30 to 5:30. So, I don't know if it's nice anymore. That's what it is. I have no choice.
We can have it on Saturday.
We do have class Monday, so we'll talk about organic metallics on Wednesday, and then just some fun and organic things. So let's jump into where we were. All right. You remember we were talking about reactions that complexes undergo, and we talked about all the reactions of octahedral complexes, the substitution reactions at least. And when we were trying to look at those, we decided whether a complex was inert or labile. Then we looked at what kind of stereochemistry it would have, and what kind of mechanism it would go by, associative or dissociative. Square planar complexes, because they only have 4 ligands, almost always go by associative mechanisms. Then they can go to a coordination number of 5 very easily. Because it's associative, the nucleophilicity, how good of a nucleophile you have, matters greatly, because that's going to be kind of one of the rate determining steps, is adding the nucleophile. The other spectator ligands also have effects on these reactions, and they're more pronounced in square planar complexes than they are in octahedral complexes. So there's a trans effect, and we'll go more into that, but that'll dictate which ligands come off, or which ligands are substituted. Steric effects, if we have a very bulky ligand, we might not actually see substitution because it might block up some of the sites. So there can be some steric effects. Basically, you don't have room for the nucleophile to come in. And then stereochemistry, because it is an associative mechanism, much like in the octahedral complex, cis or trans is typically conserved. Only exception to that is when the activated complex, the coordination number 5 complex, is really long-lived. So let's look at kind of what's happening with these transition states. And in some cases the intermediate is on here. So we have a square planar complex. Y is our nucleophile. One of the possibilities is that it comes in and makes a trigonal bipyramidal structure. And so as Y goes in, X comes off. There is an intermediate where it is 5 coordinate though. So one leads to the other. The other possible geometry that it goes through is where it's square pyramidal. This happens a lot if we have bidentate ligands that are kind of holding it into a ring, a heme. A lot of bioinorganic things are held into that square pyramidal state and react as a square pyramid with things coming on and off the other side. But the square planar, the nucleophile comes in, so it's kind of sitting on top for our initial intermediate, and then it's going to kind of bend, and either it will kick off this one and we'll get a trans, or it will kick off the other one and get a cis. So that's a long-lived transition state if we can kick off the cis. Squinty eyes. Are you seeing what's happening? in all cases, we're kicking off this green ligand, okay? Whether it's over here or over there. It just has to do with what amino the shape of the amino. Well, since they're associative mechanisms and square planar complexes are well known, they're one of the most studied complexes for looking at their reactivity. So all the platinum, palladium, and nickel compounds are well studied for substitution. And so they've actually teased out a lot of things about how these reactions work. And they've plotted all kinds of information. You can look up all kinds of information. But there's a few key points that you want to see here. This is nucleophilicity parameter. It's specific to a platinum complex, but it's how good of a nucleophile do you have? So as we're going up, we have different nucleophiles. The thiocyanate being a pretty good nucleophile. And then we're comparing things that are all pretty good nucleophiles, but kind of the worst on this list is the chlorine. So as we increase the nucleophilicity, the reaction rate increases. So that's log of KT is the reaction rate. So they were just looking at all of these different nucleophiles. You can actually get this nucleophilicity parameter, and that just tells you how strong of a nucleophile it is for platinum. That's why it's an N sub PT. So we'd have a similar ranking or chart that was determined experimentally for palladium or for nickel. If we went to palladium, so actually, let's jump all the way up. We go from platinum to nickel. Should we see any differences on which ligands are better nucleophiles? Yeah, some of those soft ligands are no longer going to be great nucleophiles because they don't overlap as well. And so we should see a change in like I-, very soft nucleophile. So it's still a nucleophile, but it's not going to be as good of a nucleophile as it is with platinum. They've also taken all kinds of different complexes and determined how sensitive it is to the nucleophile. And so this is like a sensitivity parameter. So you can see that as we increase kind of steric bulk, it becomes less sensitive to the nucleophile. Reaction rate is also going down. Main thing from all of this data is to say that we know a lot about the rates of reactions. Basically, people have thrown things together and measured the rate of reaction many, many times. And we can calculate out these parameters, but because it's associative, it's sensitive to the nucleophile strength. So one of the large effects in square planar complexes is the trans effect. And what we're talking about is if we look at our ligands, some of them are going to cause the ligand on the other side, the trans ligand, to be weakly bound. So let's say we have our platinum complex, we have a couple chlorines, we have X and Y here. Not very specific. If we're looking at a trans effect, once we get this ranking down, if we say that this is the stronger trans ligand, it's a weird term, but what that means is that the chlorine, or whatever ligand is trans to it, is likely to be substituted off. It's activating the transposition for substitution. Now, why would it activate the substitution? One is if it has a strong sigma donor. Now this is not the spectrochemical series, right? This is only how it is a sigma donor. Our spectrochemical series also takes into account pi effects. But as we get more negative over here, these are really strong sigma donors. We also know these to have other properties, but they're strong sigma donors. So if they are donating electron density to the platinum, then this bond has to be a little bit weaker. Now why would that be? Imagine the d orbital that goes right here. If this one's donating in, and it's making a bonding interaction, then there's not much of an interaction left for that chlorine. So there will be a weaker chlorine bond there. Also, if our ligand is a pi acceptor, then we're going to decrease the electron density to the metal and increase the likelihood of a nucleophilic attack. So, now we have a very different effect. The electron density is coming out here. That makes that platinum a bigger positive charge, because almost all pi acceptors are also donating to the metal, right? So notice our pi acceptors here are pretty good sigma donors. So they're donating to the metal through this sigma bond. They're taking electron density out of the metal, making it positive. So one, this is weaker, and now that metal wants to be attacked by a nucleophile. So whatever nucleophile we put in at this point is going to replace that chlorine that is opposite our trans effect ligand. This is going to change how you go about synthesizing some compounds. So, take this platinum complex. Why are we sticking with nickel, palladium, and platinum today so far? They're D8. D8 loves square planar. Okay? So, if we want to synthesize cis and trans of this complex, how do we do that? Why don't you start by making it from the chloride? Is it right there? Okay, that won't help. Okay, so if we have the chloride, if we put in an NH3, we'll make one substitution, right? There was no trans effect to that step. It just is replacing one ligand, and that is based on how much NH3 we put on. If we put more NH3 in, we'd get more NH3 substituting on. But once we get to this step, then we're going to think about which one is the stronger trans effect. Is it NH3 or is the Cl a stronger trans effect? Absolutely a Cl. So any of the Cl's actually. In fact, even the one that is opposite the NH3, so we could get a side product here that we don't want. But if we put in our NO2, it is going to replace something opposite of a chlorine. Could it have replaced our NH3? Yes. Okay. So we could get a mix of products here that we don't want. But this would be one way to get the cis. If we add in NO2 first, and substitute up one ligand. The NO2 is a better trans effect ligand. So the chlorine opposite the NO2 is going to be replaced with our NH3 when we put that in. And so we will get a trans platinum ligand. Trans chlorides.
Can you say one more time why it's cis? For the NH?
Why this is called cis?
No, like how does it do cis?
So it's going, because the chlorides are stronger trans effect, it has to replace opposite of the chlorine. So if it replaced opposite of this chlorine, that'd be an NO2. If it replaced opposite of this chlorine, that would be an NO2. Those would both lead to that product. Only problem would be if it replaced opposite of this chlorine, which would then lead to our NO2 here, not the product we want. So there'd be two possibilities of making this structure. Questions? Okay, so now start with platinum NH3, 2 plus, our other possibility up there. And I want you to make the trans. So you're just starting from a different starting material. You're trying to make trans of this. So you're trying to make this complex right here. Anybody got a first step that they like? Okay, so we got two different ligands. We can either throw in chlorine or the nitro. Okay? You go and throw in the chlorine. Okay? The first time that it substitutes, then now you're going to use the trans effect of the chlorine to place the other chlorine opposite. Now those chlorines are kind of duking it out, right? Trans effect, they're labile, but they're not more labile than anything else. So now when we add the nitro, there is some possibility that you'll get this product, right? But mostly you will get our desired trans product. What's that like for you?
Nothing, just connecting it to organic. What I can't do.
At this point, it's platinum 2, so there's no charge here. It's got a positive charge.
NO2 doesn't add with a negative.
NO2 does add with a negative. Oh, I'm sorry. Yes. Okay.
So how do you control and keep the CLs from going active?
The time that you let it react and the concentration of reactants. So you use stoichiometry to try and keep it from going all the way.
Which of those products would be typically tried?
Why not the one because that NO2 would replace opposite of it?
Right, but we've got kind of our chlorines are opposite of each other, so they're kind of canceling out a little bit. Because they're both pushing and pulling, so it's increasing the reactivity of the complex, but it's kind of canceling out some of their trans effects. Yeah.
So then, on our top row there, don't those chlorines kind of cancel each other out in the same token, and then, I mean, isn't it kind of the same case?
Well, but we don't have, so we could get that nitro here. Yeah, that was the second product that we talked about we could get.
Right.
So that could happen. But that doesn't help us towards getting this product. So but they're going to be isolatable by their charge, right? So I said make this. Not that there isn't any side products, because there's side products there. There's some side products here. This one's a little more clean. Okay. Okay. So if we don't do substitution, another thing that we could do with metals is we can change their oxidation state. So we can either do reduction. What is reduction? Gaining electrons. So what does that usually do to the charge? Decrease the charge. Okay. Oxidation.
Losing electrons.
Loss of electrons, so increasing a positive charge. Okay? So, we're going to work through this example and see if we can tell why it would be redox versus a substitution or something else. So first I want you to look at and classify how many electrons we have and whether it's a labile or inert compound.
Put that at
D5.
electrons.
Yes, D7.
Huh?
D7.
D7. Which we know that D7 is labile. But
Would it want to be D7 or would it want to lose the two that are in the D to have a half full section of D5?
just as S's. Just always
Let's do it. And just go with it and pretend.
And then we have chromium 2 plus, which will put it out at 4. D4. And D4 is a labile. It's high spin. How do we tell if it's high spin or not? There's a lot of stuff I need to figure out for that test.
It should be high spin.
Okay, so cobalt 3 plus, how many
I'm assuming
electrons
it's
do we have?
7.
It's a D6.
Really?
Yes, it is. Yes.
3 plus, because the thiocyanate has a
Oh,
negative,
that's it, yeah.
so
Yep.
don't get the negative from there. Okay, so if it's D6, it can be high spin or low spin. Which one do you think this one is?
High.
You've got all of these kind of middle of the range NH3s from your spectrochemical series, and then you have a thiocyanate, which is a pi acceptor. So that's going to make the delta bigger, which makes it low spin. A D6 low spin. Inert. So no substitution is happening with this one. What about this one? It's D4. Aqua ligands are usually high spin. Right, so this is a D4 high spin, so this is labile. Good thing, because we want to do an inner sphere electron transfer. And in order to do an inner sphere, we're going to actually have to use the ligands that we have. So we need at least one of the complexes to be labile, because it has to be substituted. Right? So what we're going to do is we're going to take off one of these, and make it a 5, and we're going to make a new ligand on there. That new ligand actually happens to be the sulfur from over here. This is inert for substitution at the cobalt, but it can use the ligand over here to bind and make a mu complex, a bridge between the two. So that's what's shown, actually right here. We have a cobalt, and then we have the nitrogen, the copper, or the nitrogen, the carbon, and the sulfur bonded to the chromium. It had to be labile because it had to get rid of one of those waters. Okay. Now electron transfer happens. Okay. So we go from cobalt 3 and chromium 2. What do we have over there? Cobalt is
2.
2, and chromium is
3.
3. But this doesn't look like just dissociation, right? How many d electrons does cobalt 2 have? D7. Okay, and then what about the chromium? D3. What about inert and labile? This is inert. D3s are always inert. So when we do the separation, right? So it's going to fall apart now. We're going to be left with this chromium that has aqua ligands, but then the thiocyanate is on there. It actually should be shown bonded through the sulfur like it is, because it changed. So that one's not going to do any substitution, even though this might be happening in water, because it's stuck there. On the other hand, the cobalt is now going to be D7 with NH3 ligands, so middle of the road ligands. So it will be a high spin complex, substitutionally labile. So even though our initial product from this reaction reaction is this. It doesn't last. Okay? Because we made a D7 high spin Labile complex in water. They all turn into aqualigens. Okay, they don't turn into aqualigens. Aqualigens substitute for the NH3.
Alchemy.
Chromium should still have 5 there. Okay, so yeah, fix that. Yeah, no, it didn't lose anything. It has to stay inert. Okay. Now on the bottom one. Take these two complexes. Decide whether they're labile or inert.
So we have iron. Is that 2 plus?
This should be a practice. That's
Cn is a negative, right? So we put 2 plus.
So that's D6.
If there's D6, and D6 can be either one, but the cyanide,
okay. Somebody tell me what the iron is.
D6.
D6. Is it high spin or low spin? It is low spin because all of these ligands are pi acceptors. They're high on the spectrochemical series. They're strong ligands, big delta, low spin. Okay. Iridium, what is it going to be?
It's originally D7.
It's iridium 4 plus. So it's a D3.
D3. Which are always inert.
It's a 2 minus, so we've got 6 negative charges here, so it has to be iridium 4 plus. If we take away 4 electrons, 1, 2, 3, 4, 5, it should be D5.
I was going to say they're both inert. My life is a lie. So I'm going to guess it's high
Okay,
spin.
they both have to be inert for this to work.
What?
Okay, so make this, how are we going to make them?
where's D5?
Make it low spin?
Where's D5?
Make them cyanos. Turn them all into cyanos.
Where's D5 show?
Because what does that do?
D4 through 6.
Oh, it's
Makes it low spin. A D5 low spin, D4 through 7 are inert. And in order to go through an outer sphere electron transfer, most of the time they're both inert. It could be labile because if we didn't have any bridging ligands, but cyanos can be bridging ligands, so we can't do that. So inert and inert, if we change this to cyanos, then the only thing that's going to happen is we're going to do electron transfer, but they don't actually go through an intermediate where they're hooked together. So that's why it's called an outer sphere electron transfer. So go to the next page, and you'll see, on the next slide, you'll see the difference between inner sphere and outer sphere. So you have our 2 octahedral complexes. For an inner sphere and an outer sphere, first they have to get close enough together. That's the precursor complex. If there is a ligand that can form a bridge, in the inner sphere it'll form a bridge. For an outer sphere, there's nothing to form a bridge. Or you've got 2 inert complexes, so they're not going to substitute, so you can't form a bridge that way. Then you get electron transfer, they separate, and you get your products. Which one do you think goes faster?
Inner sphere.
The inner sphere actually goes faster because it's easier to transport the electron across a bridge rather than through space. Having the electron jump is harder. Yeah. You have to go we are going to predict reactivity. There's a few questions that we start with. One, is it labile or inert? That was the first question. Because that'll tell you whether it's going to be substitution, redox. There's also the possibility of photochemistry. So if it's labile, then substitution is likely. If it's inert, redox is likely. If it's substitution, we're going to ask, what is the geometry? Okay, so are we starting with a square planar complex? Are we starting with octahedral complex? Those are going to change which mechanism is likely. Octahedral goes by what mechanism? Dissociative. Square planar goes by what mechanism? Associative. And then right there in the middle is the interchange, associative and dissociative interchange, which is kind of the hybrid. Then we're going to figure out what the stereochemistry will be. Most of the time, stereochemistry is retained. If it's associative or dissociative, it depends on the transition state. Ligands, we're going to look for that trans effect to see which ones are substituted. If we've got that at least one of our complexes are inert, then we have to ask, does it have a polydentate ligand? If yes, then it's going to be intersphere. So cyanos, thiocyanates, that's what I'm thinking of off the top of my head. Those are likely to be intersphere. If not, then it's likely to be outer sphere. So, what's going to happen? Work on it for a minute.
Question. There's only, oh, let me just go find my mind.
What?
Like, there's only 4. That means I'm good. We're gonna deal with this. Bye, guys. Should I be? No, that'd be 3. So do we first? Cobalt pressure. Cobalt.
Oh, I haven't looked at cobalt yet.
So that would make it iron spectra 1, 2, 6. This is D6.
D6, yeah.
And then chromium.
I think it's just D4, right?
The chromium.
Yeah, because it stays T+.
D4. Alright. So now to look at our neatness. Okay. So a bipi gives a lot. So I'm saying that's low spin. And the feeding and the energy is also. So is it inert for both of them?
I think so.
Inert. Inert. That's we are going to go by. We do have polydentates, but they're both inert. These are polydentate. So we're gonna go by inner sphere. But how do we go?
Okay, so what have you analyzed? Are they inert or labile?
Inert.
They're both inert. Okay. So being inert, what kind of reaction are we going to have?
Redox?
Redox. What kind of mechanism? It has to be outer sphere because they're both inert, right? So no substitution can happen. We also don't have a really great bridging ligand here. The bipi are bidentate, but they're not a good bridge. Okay, thiocyanate, cyano groups are good bridges. So we end up with two more inert complexes. We would end up with a cobalt 2+ and a chromium 3+, which are also inert, so we wouldn't have the substitution after the electron transfer either.
Why does the copper have the same charge? When
There's no copper.
cobalt, I mean not copper.
It doesn't. It goes from cobalt 3+ to 2+, chromium 2+
Oh,
to
okay.
3. That's when the electron is transferring. So where is the electron going?
It's going from chromium, or from cobalt to chromium. No, from chromium.
From chromium
To cobalt.
So this is the one electron transfer because we're going up in oxidation states. We lost an electron. That lost electron is going over here, reducing oxidation. And then we can also kind of look at our reactivity for substitution. This is a good one for a trans effect. Chloride or CO, which one's going to have the better trans effect? The CO. So we'll end up with an NH3 and the trans product. Now that's neutral. Yeah. We'll have CO- and NH3. Oops, we used it. Okay. There are some good practice ones in chapter 12. Okay, I can post the specific ones. So now let's play with nickel complexes. Okay, nickel nitrate. It's a hexahydrate. If we put it in water, it turns into the hexaqua. It actually does prefer the octahedral in some cases, even though it's a D8, because it's, yeah, it just does. So these are all small ligands, and we got our small nickel. So draw the LF splitting diagram. Ligand field splitting diagram. How did the d orbitals split?
2 in one place and 3 in another. Maybe.
It's octahedral should be 3 and then 2. Is that what we're asking? So it'd be do. And then, right? Is that what we're saying?
Is that what the question is? What's chemistry?
We take the d metal. The LF splitting diagram is the one that we're using all of the time,
Yay.
right? Where this one is going up by 3/5 delta minus 2/5 delta down. How many electrons do we have in this complex? 8. So is it high spin or low spin? No, the 8 gets one way to come in. Okay? Draw the angular overlap splitting diagram. How's that different? You still have the same D metal. You have the ligands. Which we didn't pay attention to in the ligand field splitting diagram. Okay? D metal still has 8 electrons. Angular orbital overlap, we use that table. 3 of the d orbitals, x, y, y, z, and x, z, do not move in energy. Z squared and x squared minus y squared, just like over here, go up 3 energy units. To balance the energy over here, we balanced it all with d metal orbitals. Over here, we haven't balanced it yet. We have a total of positive 6 energy units. So we have to stabilize these ligands by 1 energy unit. Those are still filled. And then we put in our 8 electrons. Okay? Okay, I said below and then I pasted it over here. This is the UV vis. Instead of nanometers, I made it simpler for our purposes. I put wave number here. Here's where you'd start kind of the Roy G. Biv of the spectrum. So it's kind of opposite of, so this is higher wavelength to lower wavelength because wave number is the opposite. So what color would you expect to see? Maybe green? Okay, how are we going to get that? We should see green. If we're seeing a green color, then it's absorbing,
the
opposite that, it's absorbing in the red. Red is kind of, these are a little bit too low to be visible. Red is kind of right here. Okay? So those peaks would combine to make our green color. What would this peak over here be? It's going to be kind of on this violet side. So it's going to contribute some yellow. So that's not really going to change the color because it's mostly green. Okay, so combination of the two, it will be a green color. Plus green color. It's a D8. So the lowest energy wave number transition is equal to our octahedral field. So our octahedral field is right there. Okay, that peak. So I took a guess at what it was. It's not actually labeled. Something like that. That would be our delta. Okay, because that's the lowest energy transition. Okay, so I don't understand the squinty eyes, so tell me what your questions are. We should see 3 allowed transitions for D8. To be an allowed transition, we have to say triplet to triplet. So that's why we're getting 3 peaks. This little shoulder thing is because there's different vibrational states within there, so that's why there's a little question mark there. But we would think about it as 3 big peaks for allowed transitions. And our first one, our B1, is our octahedral field.
Real quick.
Mm-hmm.
I feel like it should be going down by like half an energy unit.
Well, this is 3 times the 2,
Right?
and we have 6 here. So this is 6 energy units. And if we move 6 levels down 1 energy unit, then that would be 6 energy units.
So we're moving like 12 electrons down?
But it's the orbitals,
Just the orbit, okay.
right? So we lowered the orbitals by 1 energy unit. It doesn't matter whether they're filled or not. It's that our orbitals have to sum to the same energy. That's why we could do it over here, even if they were not filled. Right? It balances energy. Okay? and now we have different ligands. How's it going to change it? What colors are we going to see? Okay, let's watch. Green. Okay. We're gonna do it more here.
Can you move the screen as well?
Oh, yeah.
Yay.
Can you see the green now?
Yes.
Green. Okay. If we put in, let me find my direction here so I don't have the wrong thing. NH3, 20 milliliters of NH3. How should that change?
Dr. Breen
Is that a bigger delta?
Ooh.
A bigger delta, right? So I'm going to go back to another screen. So here was our delta. Now we've got a bigger delta because of the ligand, so it will move up. And that would correspond with changing to a blue color, right? We were in red, seeing green. Now we've moved over here, so we're seeing blue. Okay?
Still not sure I understand.
I know we're a little bit late, but I think it's worth it. Hopefully you'll agree once you see all this.
Yay, colors.
Okay? Okay, so now we have ethylene diamine. Right? It's still only a sigma donor. Purple if you can't see me. And so why are we seeing purple? Because we moved down this way. So what will we see over there? They would shift. Our delta is shifting. It's getting bigger.
Delta gets
Imagine
bigger,
that.
blue shifts.
Stigline.
I have no idea.
Let's see. Yep, make a prediction. Last chance to make a prediction.
It's gonna become red.
Okay,
We're gonna come for full circle.
before I add it.
I did not guess
It's
maroon.
red. It's kind of got a purple tinge to it, but it is definitely a pink. And if I swamp it with, what's our best high acceptor that we love? Cyano. Right, so if I put Casey in there.
She's such a bad influence right now. I love it.
So it becomes very orange.
It's still becoming orange.
Look, we ticked along the color wheel, seeing green all the way over to here.
What about yellow?
That was the same as increasing our delta all the way from our low delta all the way to the highest delta. So, yeah. Feel free to ask
What?
questions. It finished doing its substitution. It actually, if we let it sit, it'll go to a square planar complex because the cyano likes the square planar better than the octahedral, and so it'll change color again. Let's see, it's got to be decreased in half, so it will turn more green.